Did you read the textbook? The section says, like they wrote, the sentence says, the important thing to remember to do now is not panic. They are, yeah. Okay, so here's a linear system, negative 2x minus 3y and 3x minus 2y. Right? So here's its vector field. It does not appear to have any straight line solutions. It looks like all the solutions are kind of swirling around the origin. So that's kind of sad because the straight line solutions were what motivated all of the algebra that we've been learning for like 2 weeks now, with the eigenvalues, eigenvectors. Like the whole reason we developed that was in pursuit of the straight line solutions. But don't panic. We're just gonna, having nothing else to try, let's just do that. Nothing else in our tool belt, we're just gonna do the same thing. Find the eigenvalues and eigenvectors and just apply the same exact tool that we did when there were straight line solutions, and we'll just see what happens. Okay, so eigenvalues, we find those by taking the determinant of a minus lambda I equal to 0. So we want the determinant of negative 2 minus lambda, negative 3, 3, negative 2 minus lambda equal to 0. So the determinant is a times b minus b times c. What did I say? Did I say b? Sorry. A times d minus b times c. So this, when I square my negative 2 minus lambda, I'm going to get 4 minus plus 4 lambda plus lambda squared plus 9 equals 0. No, because I'm like foiling these two. So my first gives me positive 4, outer and inner, and last, yeah. All right, so combine my like terms here. I have lambda squared plus 4 lambda plus 13 equals 0. Does that factor? No. So we have to use the quadratic formula. So we get lambda equals negative b plus or minus the square root of b squared minus 4 times a times c all over to a. All right, so 4 times 13, that's 52. 16 minus 52, 36? I don't know, I can't do math in my head. Negative 36, yeah, that's what I meant. So we have negative 4 plus or minus the square root of negative 36 all over 2. And how do you simplify the square root of negative 36? 6i, yeah. You guys remember that? Okay, good. So we don't have to do a review of all complex numbers. So this becomes negative 4 plus or minus 6i over 2, which can simplify to negative 2 plus or minus 3i. So we have 2 eigenvalues. They happen to be complex. Negative 2 plus or minus 3i. So we can't really classify the fixed point at the origin, because the only ways that we have to classify it right now are if they're 2 distinct real eigenvalues. So we can't use those same rules as before. So we're just going to have to continue with our investigation. Let's try to find eigenvectors that go with these 2 eigenvalues. Okay, so let's look at negative 2 plus 3i. That will be our lambda 1. So I want to solve AV equals lambda V for V. So those are the eigenvectors. I'm going to replace A with the original matrix, negative 2, negative 3, 3, negative 2. And times xy equals lambda, negative 2 plus 3i, times that same vector xy. So just keep following the same process we always do with the real numbers, and we just have to remember how to do complex arithmetic as we go. Okay, so hopefully that will come back to you as we do this. So we're going to get negative 2x minus 3y equals, and then negative 2 plus 3i all times x is negative 2x plus I 3x. And then 3x minus 2y is going to be negative 2y plus I 3y. All right, so these two equations, let's simplify them. So add 2x to both sides, those go away. And I get 3y equals I times 3x. Negative, thank you. And then this equation, my 2y's go away, and I get 3x equals I times 3y. Are those two the same? Because usually we end up with, when we did this procedure before, we would come up with either one of my equation came out to like 0 equals 0, or they were the same equation. Is one a multiple of the other? Maybe I'll finish, I'm just going to say y, I divide by 3, those go away, right? So I get y equals negative ix, and this one I get y equals x over I. So are they the same? They do, yeah, but we just want to make sure that we understand why they are the same. Negative I and 1 over I, yeah. So the powers of I always equal like I, 1, negative 1, or negative I, right? So we need to see, is I to the first the same as I to the negative 1? So so let's do like 1 over I. If I multiplied this by I over I, I'd get I over I squared. But what's I squared? Negative 1. 1 over I and negative I are the same value. Yep, I over I is just a fancy form of 1. And so I just did a little trick to show you that they're the same. Yeah. Yeah, 1 over I times I over I. Because I squared is negative 1, yeah. So I over negative 1 is negative I. I'll write down the list. There we go.
I have one other I question.
Sure.
What if you have like square root of like negative not 30 or something?
Yeah, it would just be I square root 30. And then you could simplify square root 30 if it simplifies, if you want. Okay, so these two equations are the same. We just showed that these are the same. So give me a vector that lies on this line of eigenvectors. If you make x 1, what does y have to be? Negative I. So here's an eigenvector.
So I was looking at the bottom on what if you multiply both sides by I, then you got IY
IY equals X, yep.
then he said I.
Yeah, so 1I is also on there, yeah.
Oh, okay.
So that would be another eigenvector.
Oh, okay.
Yep. So, yeah. So we have an eigenvalue and an eigenvector, and I have another eigenvalue. I have to find its associated eigenvector. Let's see. I'm actually not going to do that because it's gonna turn out that we don't need it, that we're only going to need one. So rather than waste everybody's time, I'm going to tell you the punchline ahead. Okay. So since we have an eigenvalue and an associated eigenvector, I can write a particular solution to my system of differential equations, right? E to the lambda t v. Okay, so I have a particular solution, e to the lambda t b. We'll call this y, we'll call it y1, I guess. E, lambda was the value -2 plus 3i, right, was my eigenvalue, -2 plus 3i. And then my eigenvector was 1 -i or 1i. You can use either one. I kind of like 1i because then we don't have to deal with the negative. I1, yes, you're right. Okay, so we can get solutions. We could get another particular solution using the other eigenvalue if we wanted to. So here's a particular solution to my system of differential equations. So we have good news and bad news, right? The good news is we can still do it, right? We could check that this is a solution by differentiating, making sure both sides of the equation are equal. It will be. It works. The bad news is that the solution involves complex numbers, okay? Which is not so bad. We have ways of dealing with complex numbers. Yes. Yep. We're headed there. Okay, so we can still get solutions, but they have complex numbers in them. All right, so here's how we deal with complex numbers. We're going to use Eulers' formula. We derived this in Calc 2. I don't know if anybody remembers, but if you had me for Calc 2, we definitely proved this formula is true using Taylor series. E to the I theta equals cosine theta plus I sine theta. So I can do a quick proof just to remind you. So remember the Taylor series for e to the x was so e to the x had all of them, every power of x. Yeah, yeah. And then the cosine of x, cosine is an even function, so it's the one that has evens. Ooh, do the signs alternate? I think they do. So it goes 1 minus. Yeah, they would have to alternate because the derivative of cosine is always going to change sign. Cosine of 0. Yeah. Yeah. And then sine x, its first term is x minus I hope those are right. So if you replace x in this formula with I theta, because we're doing e to the I theta here, you're going to get a new series with i's and thetas in it instead of x's. And then for this one, you're going to replace x with a theta. And this one, you're going to replace x with a theta and multiply the whole thing times I for the I sine theta, and you show that the two are equal. For the sine times I, yeah. Yep. Yep, so that's sort of the general outline of how the proof works. I'll let you prove it to yourself on your own later. The proof is also in Appendix C of your textbook. All right, so now we're going to combine Euler's formula with some simple laws of exponents and to come up with a new theorem, truth. Okay. So if I want to do e to the a plus ib, I want to raise e to a complex number, which is what I want to do, right? I want to be able to raise e to this complex number. So to raise e to a complex number, I'm going to use the same trick where if I have e to something plus something, I can rewrite it as e to the a times e to the ib. We've been using that trick a lot this semester. A is the real part of your eigenvalue. Yeah. Right, in this case it would be -2. Yeah. Well, this whole thing, this whole complex number is to the t. So this would be e to the a t plus ibt. Yeah. So no t's right now. We're just figuring out how to raise e to a complex number. All right, so now I have e to the a. Apply Euler's formula to e to the ib, right? Because e to the I theta was cosine theta plus I sine theta. So this is cosine b plus I sine b. And then you can just distribute the e to the a. So we have e to the a cosine b plus I e to the a sine b. So this is how we raise e to complex numbers. Okay, we are able to take e to a complex number and write it in the standard form of a complex number, x plus iy. All right, so now we're going to use that new truth that we derived to rewrite one of the particular solutions we found. We actually only found one because I stopped us to save a little time. So my particular solution was y1 of t was e to the lambda tv, e to the -2 plus 3i t, and my vector was I1. Okay. All right, so I want to use this to rewrite my solution. Instead of having e to a complex number, I'm going to rewrite it. So this is going to be e to the -2t plus 3ti, just distributing the t. Then I'm going to apply my rule of how I rewrite this. This is going to become e to the a cosine b. So that would be e to the -2t cosine 3t plus I e to the -2t sine 3t. All times the vector I1. You mean instead of 1 negative I? Yeah.
No, like this is
Yeah. I'm rewriting the solution in a different form. Yes. Yeah. Yeah, so I'm not doing any more solving, right? I had the solution. I'm just trying to rewrite it into a form that we're more used to looking at. Like an A plus BI form. Yeah. Okay, so this whole part, this big thing here, gets multiplied times each component of the vector. So this is going to become one big vector, I e to the negative 2t cosine 3t plus I squared e to the negative 2t sine 3t. And then the next part is just times 1, so it stays the same. E to the negative 2t cosine 3t plus I e to the negative 2t sine 3t. Okay, lastly, I'm just going to replace I squared with negative 1. And I'm going to put, as the custom is, I'm going to put real parts on the left, imaginary part on the right, so it looks like A plus BI. Okay, so this becomes, I squared is negative 1, so I have negative e to the negative 2t sine 3t plus I e to the negative 2t cosine 3t. And this one stays the same. Okay, last thing I'm going to do. Yes. Uh-huh. No. I am going to break this into two matrices, but just with simple addition. I'm going to break this into the real piece plus the imaginary piece. So this is going to become negative e to the negative 2t sine 3t, e to the negative 2t cosine 3t. That's the real part of my solution, plus I times, so I'm factoring out an I, the imaginary part of my solution. E to the negative 2t cosine 3t, e to the negative 2t sine 3t. So this is just, nothing amazing has happened here. I just rewrote the formula that I found using my complex eigenvalue. So now I have, the standard format that we're used to working with complex numbers in. A plus B times I. Yeah, you were used to it at one point, at least. Okay, so this was a bit of work. However, it pays off because an amazing fact. If the linear system has a complex solution, y of t has a real part plus I times some imaginary part, then the two parts, the real part and the imaginary part, are both themselves solutions to the system. So then we can use the real part and the imaginary part as our two particular solutions. No, because no, not really. So what I now have is that this matrix is a solution, right? And this matrix is a solution. Yes. We don't have a general. We don't have a general. We just found one particular solution. Yeah. This was just the one particular solution that corresponded to our complex eigenvalue. Okay. So that means once I have my one particular solution written in this form, I can just grab these two vectors, and now I have two particular solutions, that neither of which has complex numbers in it, right? Because I factored the I out, and it's the thing without the I that is also a solution. Yep, just grab this vector, and you have two particular solutions. So that's going to be e to the negative 2t sine and then my other solution, yes. Oh, yes, thank you. And then the imaginary part, where I have factored out the I, right? So my original solution was y real plus y imaginary. This amazing theorem says that y real and y imaginary, with the I factored out, are two particular solutions. I'm going to talk about it in a second. First, I just want to show you, and then I'll talk about why. Okay, so this one, e to the negative 2t cosine sine. Okay, two particular solutions to the system. So right now I'm just telling you, it's kind of magic. This is how you can get two particular solutions. I think about it as y of t, the thing we found, is really a linear combination of two other solutions, so they would have to also be solutions. I is the coefficient, so like when you have a linear combination of two, yeah. Yeah.
Well, y of t is not a general solution.
Yes, true. Yeah. So okay, so let's prove it. Let's prove to ourselves for this particular case that these are both solutions. Verify for our example. So this is a good thing that you could do in your groups. Show that both of those two solutions are solutions to the original system, y equals, say it again. Okay, show that our two particular solutions make this true. It works, okay? So the actual proof is in your textbook. I don't really want to do it's just a computation that shows that these are both going to be solutions. So you can read it in your text if you want. So we also want to make sure that these are linearly independent solutions. Just check their initial values. So if I plug 0 into my y real, I get -1 times the sine of 0. What's the sine of 0? 0. So I get 0, and then 1 times the cosine of 0, which is 1. So I get 0, 1. As my initial value for y real, and then y imaginary at 0 I'm going to get 1 times the cosine of 0, which is 1, so I get 1. And then I get 1 times 0, which is 0, so I get 1, 0. So are those two vectors linearly independent? Yeah, they point in, they're not on the same line through the origin, they're not multiples of each other, they are linearly independent. In general, from now on, you won't have to check this. When you have two complex eigenvalues, the real and the imaginary part solutions will always be linearly independent. So we've got two particular linearly independent solutions. What do we do with them? Yep, add them up, throw in the k's. We're going to have a y general, put a little g for y sub general. That's going to be k1 times this y real plus some other k2 times the y imaginary. And then we could write them all out. Well, okay. K1, y real, that's negative e to the negative t sine 3t The I disappeared, yes. Yep, so that was the magic of using Euler's formula to rewrite our solution that had complex numbers in it. Once you can write it as A plus BI, you can pluck off the A and the B part, and you have two new solutions. So there's our general solution. So the trick of using the real and the imaginary part of a complex solution means that you only have to find the eigenvector associated with one of the eigenvalues. So you just trade some hard work for a different kind of hard work. But it's not, one problem isn't really easier or harder than the other. So just making a slight adjustment, we can still use eigenvalues and eigenvectors to find the general solution to a linear system that has complex eigenvalues, even though it doesn't have straight line solutions. Okay, so here's a phase portrait for a linear system with complex eigenvalues. This is the system we've been working with for our example. The vector field appears to spiral around and towards the origin. So if we reconcile this picture, the fact that it's spiraling and approaching 0 with the formula, I happened to graph the x of t and y of t for one initial condition. Yeah, that's why I put it in there, to remind myself to show you how to do it. Okay, so my system that I've been dealing with is negative 2x minus 3y. Oops, number lock was negative 2. Nope, minus 3y. And 3x minus 2y. Okay, so I want vectors, and go ahead and plot. All right, so then I have shown you before, pull up the initial value problems, and we want the dx dt trajectory. Okay, and you can either type in a particular initial value here in the x, y box, or you can just click on an initial value, and it draws a solution curve. So I'm going to delete that for a second. And then if you go to, I think it was in miscellaneous, differential equations miscellaneous, look at the x, y of t window. So this is going to graph on the same set of axes, x of t and y of t. So you open that, and you get this. And then if you click on an initial value, it traces the phase portrait in one window and the x of t and y of t solutions in the other. And let's do another one, like, kind of cool, huh? So it's under miscellaneous. Okay, so when we look at my solution, this is my general solution that I found a couple minutes ago. It is sinusoidal, right? Each of my two functions, x of t and y of t, are sinusoidal because they are made up of a sum of sines and cosines. What is the period of those two sinusoidal functions? Anybody remember? Pi, I'm here. 2 pi. Yeah. So the period of a sinusoidal function is generally b over 2 pi. And b is the coefficient on t. That's the argument of the sine or the cosine. So in our case, it would be 2 pi over 3. Yeah, sorry, it's 2 pi over b. It's 2 pi over b. 2 pi over b. Right, but they have the same input. They all have 3 t's. If it was different, then the period would not be constant. Yeah. But in all of our cases, they'll be the same. Yeah, that's true, actually. Yeah. All right. So what can you say about the amplitude of these two sinusoidal functions? It's decreasing. Yeah. So, well, we have these k's that are making it not constant, but e to the negative 2t is definitely going to 0. Okay, so I have sinusoidal activity, that's circling the origin, right? And the amplitude is going to 0, that's circling the origin and approaching 0. Okay, so my general solution is made up of an exponential decay and something sinusoidal. So that's why I have the two distinct behaviors, circling and heading towards 0. All right, so let's think back to all the work that we did to find this general solution. What exactly was it that made this amplitude this exponential decay function? So the question is, to be more specific, where'd that negative 2 come from? From lambda, right? Because lambda was negative 2 plus 3i. So it came from the real part of lambda. Okay, just the real part. So it's the real part of lambda that determines whether or not our amplitudes decay towards 0 or grow towards infinity. And what if the real part were 0? The amplitude would do nothing, right? And I would just have circles around the origin that don't grow or decay, they just cycle. So here's the summary of what happens with different kinds of complex eigenvalues. Yep. If the real part of lambda is positive, it's going to spiral out from the origin. If the real part is negative, it spirals in towards the origin, and we call it a spiral sink. When it spirals out, we call it a spiral source. If the real part is 0, then the solutions are periodic, and they repeat the same closed curve over and over. No. Why not? Like, so the question is, could you have a lambda 1 be like -2 plus 3i, and lambda 2 be -2 plus 5i, something like that? Or +2 plus 5i, or anything like, is it possible to do it for that to happen? Why not? We're solving a quadratic, right? And when you solve quadratics, your zeros always come in conjugate pairs. So if -2 plus 3i is one of your zeros, the other one has to be -2 minus 3i. Okay, they always come in conjugate pairs. Okay, so we can basically classify the origin, the type of fixed point the origin is, strictly by looking at lambda, without even finding the general solution. We know what the phase portrait is going to look like. And to decide whether it spirals clockwise or counterclockwise, right? Because we know it'll spiral out or spiral in, but we don't know which direction. Just plot like one vector in the vector field, and then you say, oh, if the vector points up, right, then you go, oh, it has to go clockwise, counterclockwise. Yeah. And then periods, 2 pi divided by b. And your book also asks you about frequency, which is just frequency is the number of cycles that the solution can make in 1 unit of time, which makes it the reciprocal of the period, right? Because the period is how long it takes to complete one cycle. So it's just b over 2 pi is the frequency if they ask you about that. Okay, so time for you to try.